Hello, everybody. This is going to be a not so quick demo about that's going to introduce K-Mer counting, which is going to be the next lab. And so much like a cooking show, I've created a few functions ahead of time that'll be useful so that we can do this in hopefully a semi-quick way. So first of all, let's get right into it. Let's talk about the reason why this video is being shot in the first place is because of the COVID-19 pandemic. So let's read in the virus that causes that disease. So first of all, SARS-CoV-2, severe acute respiratory syndrome. CoV stands for coronavirus. I guess it's normally written like this, but it's the Java identifier, I made it all caps. Coronavirus comes from the sort of, it looks like a crown around it, like the corona of the sun. Two references that although it's a different virus, it's similar to the SARS that came out in 2003 that most of you are probably too young to remember. So let's print out. Let's start to. I want you to imagine we're, remember when the cholera studio. I had you imagine you were in 1850s London, trying to get to the bottom of the cholera outbreak. Right now, we're going to just try to find some signal in this noise. Now, the people who are working on vaccines for this virus are doing much more sophisticated things than what I'm going to show you right now, but I want you to imagine we're just sort of digging into this virus. We're going to look for some signal and try to find some things that stand out. So, for example, the first thing we can do is find out how long it is. So at least this read of the SARS-CoV-2 virus came out to be 29,910 long, so that's how many bases there are. I could try to print out the actual data. I don't know if everybody knows this, but arrays in Java are sort of comically, they give out comically bad two-strings. Sort of like the type, at least at the front, that it's a byte array, and then add, and then it's, I believe that's its identity hash code, which is its original location in memory. We can print out this two-string. Sorry, not I'm just going to deep two-string, although I'm sure that would work as well. Two-string of the data, at least print out two-string of the data. Will print out all of the array values. These are the ASCII codes for A, C, T, and G. There's a couple of other values in there. I kind of just want to say new string so I can see the A, T, C's, and G's, and then I'll take the byte array and convert it directly into this. And so let's go ahead and just start to just do the most basic thing I can imagine, which is to do the nucleobase counting thing that we did earlier in the semester. So right away, let me stop printing this out because it's only so useful. Right away, we're going to go in and just launch a V5 app. And for each nucleobase and nucleobase.values, I guess I can just, well, let me just count it. So int count equals, and let's fire up lab one's nucleobase counting. We'll count n-way split, pass it the data, pass in the nucleobase that I'm iterating over, and then the number of available processors. Or runtime, I get runtime.available processors, maybe multiply by 4, since that's a number between 2 and 10. We'll count it up, and then I'm going to just print out the formatted string here of an S %D. Okay. And the arguments to that formatted string are going to be the nucleobase itself and then the count that I just count up. So if I run this, you'll sort of see that there's 8,956 adenines, 9,596 T's, like 5488 C's. And so sort of the very first thing very first thing I can do when I'm looking at this thing is sort of just know the A, T, C's, and G's. There should be at least one question that a lot of you are asking right now. I want everyone to pause and sort of look at this output and sort of see if anything strikes you as strange. Okay, and so we're back. Hopefully at least a couple of you were like, hey, what is this being 0, I thought this was a virus. Shouldn't this be RNA? Like, why are there no uracils? That's what this cDNA stands for. It's a complementary DNA. I guess RNA is harder to copy than DNA. So one of the first things I'll do is sort of just convert the virus into DNA, and then it can be easily copied and everything like that. So and read. So what this is the virus converted into complementary DNA, and that's why there's no uracil. There are also this interesting bonus situation. We put the print back in here so we can see the full data. There's this 4 non-specific. There's actually 7 misreads, and if you tunnel into you can sort of see this sort of a common thing that happens at the beginning and ends of a read. You'll get problems. So right here, there's a W, there's an M. And if you tunnel into Nucleobase, I actually have a link to University of Michigan site, which sort of breaks down the FASTA format. And M is like, when it's reading, it's like, I'm not sure if this is an A or a C, right? And it's like, rather than just guess, it'll tell you like, I'm not sure enough to tell you, I'm gonna make that. N is for sort of nondescript. It's like, could be any of them. And so if I wanted to add in one of these, like, let's say we did, I added in A or C, not sure. And I think, what does that say? Like, that's M. You'll see now when I print that out, that'll also be one of these. And one of the things we're going to do is we're going to look for some signal noise. If you're looking for signal, like, there it is, like there's the poly A tail. And I would bet you this, these N's and this D, which can be G, A, or T. I'm going to bet that those are A's too. We're not going to bet or guess. We're only going to count the things that we know. Now, we could just pull them out, but then you would be getting sort of bad information where you'd be like, oh, like I would think that was 6 straight A's when it's not. So we're going to split, we're going to not only remove them, we're going to split it up into subsequences before we do K-Mer counting so that we can only get true K-Mers. To be clear, there is a K-Mer here, we just don't know what it is, so to try to count it seems ridiculous. So let's go ahead and do that. So what I'm going to do, I'm going to take out the big long print again. I can bring up the format itself. It's over in, let me see, it's in bioinformatics. Right here, this is the data that I got from the NIH. So let's go ahead and split this up first. So I have a function that will do this for you. I try to take all the sort of annoying little parts out of this class and just do them. I'm going to make this sequences equals FASTA split utils split into subsequences of the data itself. Let me just really quick before we get going, write sequence and sequences. Just print the length of these. I could print out the strings too, but let's just print out the sequence. And I did it as sequences twice, which is not what I wanted. Dot length. There we go. And if I print these guys out, you'll sort of see this is very typical. It sort of has, it gets, this is the total length. And then it has a little problem at the beginning, and then it has a really long run, and then it has some problems at the end of the file. I guess sometimes on a chromosome, it'll have trouble with the centromere also. But we're going to try to count everything we can. There's going to be a lot of really good data in here, and then it gets a little choppy at the end, and the beginning and the end. So let's start. Let's do. So we've counted up the. This is our nucleobase counting, like lab 1. Let's start K-Mer counting this, and the first thing we'll do is we'll count K equals 1, and hopefully those will be the same values, right? And so you're going to build a bunch of K-Mer counters in this studio. The simplest one is just a warm-up that is going to be a new string hashmap painter counter. And I'm going to show you how it's used in this demo. I'll give another demo later that shows how to build one of these. But this, the K-Mer counter has the ability to produce a K-Mer count. which is going to keep track of all the different nucleobasic lines. If I call the K-Mer count, counter, why did this thing, oh, sorry, this thing right, dot parse. And if I parse these, and let's set int k equal to 1 to start, because we're just going to see if we can get it right. Then I can, this will hold all the different ones that it finds. Now, it's going to find like all the, like A, T, C, and G are all going to be in here. But we'll know how many of each one of them they are, and hopefully it'll line up with our lab 1 answer. And so in order to make this more useful, I wrote a function that will convert it into an integer. Excuse me, into a map from string to integer, because this is going to sort of stay in this byte array value situation. So I'm going to make that a map, and I like to map that takes one of these things. I can tunnel into it real quick. I just, K-Mer counts are iterable of the bytes. These are the K-Mers that they actually are. You can then take that and look it up by its count. So if I go back here, you can sort of see, I iterate over the count that gets passed in. I build a map first, iterate over all the K-Mers that are found. I convert it to strings, so it'll be nice and easy to read. And then I look up that count and return the whole map. So if I run this now on this, I need to actually do this where I print it out. So I convert it to the map. If I just print out that map, we'll see that these sort of line up. A is here, that's the same 8, 9, 5, 6, all these things line up. Again, to try to make things a little bit simpler, I looked up online. This guy gave me, this guy or gal, whoever answered this fantastic site. I don't know if you know about it, probably do, Stack Overflow. And sort of the answer to the question of how do I take a map and turn it into something that is sorted by value, which is what I want. I want to sort of sort the most common ones on top, right? And so attribution is always valuable, even during a pandemic. So I wrote this to sorted by value. I actually had to flip it around because I wanted it in reverse order, but figure we would do it this way. This thing is to sorted value of map, and that's going to make a list of entry of string to string integer, and that's going to be sorted by value. And now if I print out sorted by value, sort of see the top is at the top, which is nice. I actually wrote another function that will hopefully print this out even a little better. I have a title. Title, in this case, we need that formatted string that goes K is %D for now. I'm going to add more to that in a second. And that'll be K. And we'll do title, and then sorted by value is going to be the entries. Now let me print them out. You can sort of see, all right, so you can sort of see the T's sort of lining up. They have the same one, but this is going to become more handy when I start to loop over this. Okay, so that, at least this thing is correct for the first, for K equals 1. If I do K equals 2, you can see that, you know, you're starting to get lower numbers on each one, but they should all add up to whatever appropriate amount. It's not exactly the number because of n minus k plus 1, but it's not exactly 29, 10, but it's getting there. What I'm going to say here is that you can see sort of there's, I'm going to bet all 16 possibilities are here. When I do k equals 3, they're probably all here, but this is going to be, there's, you know, sort of 4 to the k. There's 4 to the 3 possibilities now, right? And you can see TTT and AAA are prominent. TTA is showing up quite a few bit, a lot there too. Let's start to loop over this. So if I say for int k equals 1, k less than, let's say 16, plus k, you could imagine the amount of printing would start to get to be a whole heck of a lot. So let's do one thing really quick, which is we're just going to print out the first n of them. Actually, we're just going to print out the top 10 most common ones. I just took the sub list from 0 to the size min of that with the number I want. So now it's going to go through and run through them all and sort of print out the common situation. You can see the poly-A tail showing up very prominently relative to all the other ones. That's because that signal in this noise, it actually has meaning. It helps to provide stability, I guess, during transcription. So what I want to do is make this thing a little bit more clear. So it's kind of interesting. There's 7 of these at k equals 9. There's, the poly-A tail is definitely something like how much of a big deal is it that there's 7 of these, right? Because that's what I'm trying to do, is I'm trying to find some meaning in this. There's a couple of pieces of information that can help me sort of figure out what I want to do is compare this number versus how many am I expected to find? If it was just, is this just random that there are 7, or is it a big deal, right? Because up here, right, that's a lot of T's, but like there should be about a quarter of these are T's, right? There was 19,000, so like, like how big of a deal is bar? Like it was 29,000, so it should be what, 7,000 and some. So like how big of a deal is it that is 29,000 versus this one down here where there's 7 of these? Like how big of a deal is that? So the first thing I'm going to do is do something where I calculate the total. We're going to call this total, or we're going to call it sum K-Mers in this data, okay? And that, I actually have a utility for you for this, K-Mer utils that calculates sum of all K-Mers, takes the sequences in K. If you tunnel into this, what it does is for all the sequences in here, it just figures out n minus k plus 1. So like how many are going to be in this sequence? Is that number greater than 0? Because like if you have a sequence that's 3 long and you're trying to count the 100 mers, you don't want to subtract, like they're just 0 in there. So like skip those. So this is just summing up for this particular piece of data, how many K-Mers are there in total, okay? The other interesting piece of information is like the possible K-Mers. And that I also have a utility, K-Mer utils that calculate possible K-Mers for a particular K. And this has no bearing on how long or how, like if you're doing the X chromosome, the Y chromosome, just this tiny little SARS-CoV-2 virus, whatever it is. If you're counting the 1 mers, there's going to be 4. If you're counting the 2 mers, there's going to be 16. If you're counting the 3 mers, there's going to be 64. It's just 4 to the K. Now I did this by doing a little bit shifting, but it's just 4 to the K is that answer. Like that's how many possible K-Mers there are. And what's of some interest is how many am I expected? Like what is the expected count for any particular one? Well, that's going to be the sum of K-Mers in this data divided by, and I got to convert it to a double, right? The possible K-Mers. So every single K-Mer, just if it was random, would show up 1 over the possible K-Mer. Like each one would have a 1 over possible K-Mers amount. There are this many total K-Mers in there. So like if I count it all, I should find that many. That makes sense? So what I'm going to do is here, when I'm doing this format, I'm going to say that, and I'm going to say expected is, and I'm going to just print out the values themselves first, like %d equals some float. And I'm going to say the sum K-Mers in this data divided by the possible K-Mers, and then give the expected number. And now when I print it out, I get to see, all right, so like at this thing, I should expect to find like 0.00028 of each one, and there are 19 of the poly-A tail at 15. When I come up here to this 7, right, I'm expected to have like each K-Mer should exist like 1/10 of, I should find much less than 1, like 1/10 of a chance that it's even 1. So this is the, right here at 7, each one should exist about 2 times, right? And the poly tail is 27, and this guy's 21. And so This guy right here standing out at 5, right, when it really should be this tiny little number, right? 0.02%, you know, is the expected value. And look at this, well, the polyetail is 24. This one is 5, right? And the polyetail is even more because, like, I'm telling you, those last ones are A's, right? And so this is just a very sort of primitive tool to try to find out some signals in this noise. And hopefully you will all enjoy this lab.